Hi. I guess that most of you encountered Ohm's law in high school. Now, Ohm's law states that the current I through a conductor between 2 points is directly proportional to the voltage V across those 2 points. The capital R in the denominator is the resistance of the conductor. Now, this physical law gives us a relation between electrical current, voltage and resistance. The electrical current depends on the voltage and on the resistance of the conductor. If the voltage increases, then the current will increase as well. Now, however, if the resistance would increase, for example, because the temperature of the conductor increases, then the current would decrease. So apparently the electrical current depends on the voltage and the resistance. Now this is why we will call I the dependent variable in this equation and V and R the independent variables. In the equation that you see on the screen right now, y is the dependent variable. So here, y is a function of x, and therefore the value of y depends on the value of x. And the variable x is in this case the independent variable, and y is the dependent variable. If an equation is written in this form, so y equals some expression of x, then we say that this equation is an explicit function. You have an explicit formula that allows you to determine y if you know the value of x. Now, you are not always so lucky, so sometimes a variable y is implicitly defined by a variable x. Take a look at the equation on the screen. There we have a relation between y and x, but the equation does not give us y as a function of x. The graph that you see here is also not the graph of a function, since for some values of x, it is not possible to find a unique point on the graph with this particular x coordinate. Take, for example, the blue points. Both have the same x value but a different y value. Even though this figure is not a graph of a function, we can separate it into two parts that actually are graphs of functions, the upper part and the lower part. We can even find the functions that describe these two parts by solving the equation. We find that y is either equal to the positive root or the negative root of x to the power 5 plus 4 divided by x. What you see now is the first version of the implicit function theorem that we will take a look at. It tells us that whenever we have an equation in x and y and a point AB that satisfies this equation, and for which the partial derivative with respect to y is not zero, then we can describe y as a function of x in the vicinity of that point AB. Now you might wonder why it is important that the partial derivative with respect to y is not zero. Well, let us take one more look at the previous graph. The partial derivative with respect to y in the blue point is equal to 0, and indeed it is impossible to describe y as a function of x near this point, because we will always have x values for which there are multiple corresponding y values. The theorem that you see right now is a more general version of the previous result. And in this theorem, we do not look at curves in the plane, but at figures in Rn defined by an equation in n variables. Think, for example, of a surface in R3. This particular result tells us that whenever we have a point that satisfies the given equation and in which the partial derivative with respect to a certain variable is not zero, then in the vicinity of that point, this variable can be defined as a function of the other variables. I must admit that this theorem looks a bit complicated, so let us look at an example. On the screen you see a sphere with radius 1 centered at the origin. It can be described by the equation x squared plus y squared plus z squared equals 1. The partial derivative with respect to z is in this case equal to 2 times z. So this means that for all points for which z is not 0, z can be described as a function of x and y. The points for which z is actually equal to 0 are exactly the points on the equator. Now for points on the upper part of the sphere, z can be written as the root of 1 minus x squared minus y squared. And for points on the lower part of the sphere, z is equal to the negative root of 1 minus x squared minus y squared. Well, That's all for now. I hope you enjoyed this video. I hope you learned something, and I will see you in class.